In the last video, we talked about the Haber process and how it takes place, and I've left this up from the last lesson so we can just review it again. The Haber process is used to make ammonia. We need ammonia because it's used to make fertilizers, because nitrogen is an essential element in plant growth, especially in forming proteins, and plants can't take in nitrogen from the air. They need it in the form of nitrates or ammonium ions, a soluble form that they can dissolve into the water and soak up in their roots. So Fritz Haber came up with the Haber process by extracting the nitrogen from the air and making hydrogen from natural gas. He then cleaned the gases, compressed them and heated them, and then reacted them over an iron catalyst. Under these conditions, removes the ammonia by liquefaction, by cooling it and compressing it until the ammonia turns to a liquid, and then the leftover nitrogen and hydrogen are recycled. So I want to look at two aspects of this: the rate of the reaction, how fast the nitrogen and hydrogen react to make the ammonia, and then the equilibrium. Equilibrium is going to be reached because we've got a reversible reaction. So just we're going to have a little bit of topic 8 revision here. Collision theory states that in order to react, particles must firstly collide, and secondly they must collide with sufficient energy, what we usually call the activation energy, E little a. You might remember drawing these kinds of diagrams, these energy profile diagrams. Where the reactants are somewhere here and the products are somewhere down there, and there's a big bump in the way, and the energy required to get the reactants up to the top of that bump is the activation energy. So why are these conditions used in terms of rate? What is it about these conditions which make the rate of reaction fast? Well, first of all, we'll actually start with the temperature. We've got a high temperature. 450 degrees is pretty high. What happens at higher temperature? Well, the particles have more energy, and let's be really specific, they have more kinetic energy. If particles are moving around faster, that means they're going to hit each other more often. We'll say that in slightly more scientific language. We'll say that increases the collision frequency. And more important, actually, more particles will have the activation energy. So in other words, when the collisions occur, they're more likely to turn into reactions. So more particles have energy greater than or equal to the activation energy. So that will give us more successful collisions. So 1s or 2 in successful. I can never remember. Make a comment underneath. Okay. So high temperature is going to be good for rate. 450 degrees will definitely speed things up. Let's deal with the pressure now. 200 atmospheres, 200 times atmospheric pressure. Sure, we'd agree that's pretty high. What happens at high pressure? Well, there's more particles squeezed into the same kind of space, or the same number of particles are squeezed into a smaller space, whichever way you look at it. More particles per unit volume is how I would phrase that. And giving us a kind of mosh pit effect, lots of people crowding together, bouncing around is going to increase the collision. Remember, not just more collisions, but increases collision frequency. Okay, or more collisions per second. If you wanted to put it in those terms, that's what frequency is, number of events per second. And lastly, what about that catalyst? Well, as we know, catalysts provide an alternative pathway for the reaction to take place, or an alternative route with a lower activation energy. That really makes it a game changer. So in other words, the reaction might still happen without the ion catalyst, but you'd have to heat it up to like 3,000 degrees or something ridiculous. With the ion catalyst, 450, which is much more acceptable, it is doable. Okay, so all of these factors seem to be giving us a faster rate of reaction. Okay, now we need to look at all of those factors again, but this time from the point of view of equilibrium. And it's important to keep these things separate. Rate of reaction is about how fast reactants turn into products. We're looking at well, we'll get into A level and how we measure it, but usually it's measured in the number of moles of ammonia that you make per second, or the concentration of ammonia that you make per second. Equilibrium is something different. It's about where the position of the reaction lies in terms of, is it stuck on the reactants, or is it stuck on the products, or is it somewhere in between the two? The important bit of chemistry that we need for understanding equilibrium is Le Chatelier's principle. Le Chatelier's principle states, reactions in a state of dynamic equilibrium shift their position for a change to the conditions that minimize the change. Okay, minimize the change. That's the important bit. From that, it's the bit you need to remember. So remember, Le Chatelier's principle is the idea that you put you put a thick coat on in the morning, you go out because it's cold. As it warms up, you need to minimize that change. You're going to get too hot. You take your coat off in order to cool yourself down. The day's getting hotter, you cool yourself down. You're kind of doing the opposite in order to stop yourself from getting heated up. That's the idea. And whilst that makes complete sense for somebody wearing a thick coat, it seems surprising that nitrogen, hydrogen and ammonia can organise that as well. And I don't want to get into why that is. But let's look at the same factors again, but now from the point of view of equilibrium. So if we increase temperature, that shifts the equilibrium position in the endothermic direction. In other words, to reduce the added energy. So that's always going to be true. An increase in temperature will always shift any equilibrium in the endothermic direction. The reason for that is endothermic reactions absorb energy. That's the definition of endothermic. So if I'm adding extra energy, the endothermic reaction will absorb that extra energy. Now, when we look at the Haber process, it's exothermic in the forwards direction and endothermic in the reverse direction. It's always true that if it's exo one way, it's endo the other way. That's always the case for all reversible reactions. This is exo in the forwards direction, so therefore it's endo in the reverse direction. So that means that if we increase the temperature, it shifts the equilibrium position in the endothermic direction, which means making more nitrogen and hydrogen, therefore less ammonia. So this will decrease the yield of ammonia. Now we're talking about yield now, not rate. Increasing temperature always increases rate, but in this case, increasing temperature decreases yield. What do I mean by yield? Well, let's imagine that I've got this reaction running and 50% of my mixture is ammonia and 50% is nitrogen and hydrogen. If I increase the temperature, that yield will go down. So that's going to cause us a problem, right? We want the temperature to be nice and high, but if it's too high, my yield will be too low. But hang on, if the temperature's too low, the rate might be a bit slow as well. So we're sort of stuck in a fix here, and 450 degrees is the what we call the optimum temperature, or we could say it's a compromise between rate and yield. In other words, a higher temperature would give me a faster rate but a lower yield. A lower temperature would give me a higher yield but a slower rate. So it's like a sweet spot right in the middle where we get enough ammonia being formed and ammonia being formed quickly enough to whatever we do, make money, basically, isn't it? That's what it all always comes down to. Okay, temperature is the really complicated one when it comes to equilibria. Because every reaction's different, we need to look carefully at the situation there. Okay, let's look at a pressure. Well, an increase in pressure, according to Le Chatelier's principle, not favours, we don't say favours anymore, shifts the equilibrium position to the side with fewer moles of gas. What's going on there? Well, any gas, whatever it is, occupies the same volume at the same temperature. So if I have 1 mole of nitrogen at room temperature, that will occupy about 24 decimeters cubed. 3 moles of hydrogen would occupy 3 lots of 24 decimeters cubed. In other words, it doesn't matter that hydrogen's a different gas from nitrogen, they'll occupy the same volume. So if I had 1 of those and 3 of those and 2 of those, I would have 1 volume of nitrogen, 3 volumes of hydrogen, that adds up to 4, and 2 volumes of ammonia adds up to 2. 4 is bigger than 2. Increase in pressure shifts the equilibrium position to the side with fewer moles of gas. 2 is smaller than 4. Notice that all I'm doing to work this out is looking at balancing numbers. 1 and 3 make 4. 2 is less than 4. So the side with fewer moles of gas is the right-hand side. So the equilibrium in this case will shift to the right, and that will increase the yield of ammonia. Yay, great. So increasing pressure gave us an increased rate because increased collision frequency, and it gives us an increased yield. So this one's win-win. Unlike temperature, where we needed to find that compromise, here we don't need to worry about compromise. And hang on, if we don't have to worry about compromise, why stop at 200 atmospheres? If a higher pressure gives us ammonia faster and gives us more ammonia, then 300 atmospheres, 1,000 atmospheres, why don't we just have as high a pressure as we can? Well, we still have to compromise, right? Because we're living in the real world, we're industrial chemists, and we have to pay for stuff. And squeezing gas into smaller spaces, that takes energy. So we now have a compromise, not in terms of rate versus yield, but in terms of energy costs, or the containers. Of course, higher pressure containers will have to be made of stronger steel. They're going to cost more money. Also, if we work at higher pressure, that's got health and safety considerations, right? We're going to have staff who are well trained and can deal with those high pressure situations in case anything goes wrong, God forbid. So we still have to have some sort of compromise there. And the same would be true for temperature as well. It wouldn't just be about rate and yield. We'd have to think about the energy costs of increasing the temperature up to 450 degrees as well. Okay. Last but not least, catalyst. Well, this is very quick. Catalyst has no effect on equilibrium position. The reason for that is it speeds up the forward direction, as we remember, but it also speeds up the reverse reaction. So the effect kind of cancels itself out. The only thing a catalyst would do is enable us to reach equilibrium more quickly, but it doesn't affect anything to do with the equilibrium position itself.